Hi, welcome. Let me begin with some sincere apologies. Originally this talk was scheduled for 2:50 and it was moved and I didn't get the memo. So I apologize to everybody. I'll make this worth your while, hopefully, and we'll move pretty quickly and get going. This talk is the power of intelligent flows, doing real-time IoT botnet classification using Apache NiFi. If anybody's in the wrong room, I apologize again because you waited for the wrong talk. Who are the two folks in front of you? Unfortunately, my colleague Andre de Fuchs Miranda was not able to attend, but he was a collaborator with me on this project, did a substantial amount of the work, in fact, and he is an expert on cybersecurity. He is also an Apache NiFi PMC member like myself. We're both committers on the project. We'll begin with a brief history of the problem set and what we were facing, how we tackled it, what we came up with, and hopefully time for questions at the end. So again, Andre, PMC member, really likes logs. He loves diving in and doing forensics and analysis. Myself, I am focused on security, but within the application development and penetration testing area. So working on NiFi, trying to strengthen it, trying to ensure that the application and the platform solve cybersecurity problems in the real world. I don't know who's familiar with the concept of the botnet kill chain. So kill chain was a term that originated in military usage, but in this case, we're not trying to attack people or tangible objects. We're attacking botnets. And botnets are attacking us. So a botnet, for anybody who's unfamiliar, a coordinated group of systems that are trying to use and infect and use systems they don't own for their nefarious purposes. From the perspective, this is moving linearly in time. So from the left, we're looking at the early stages. We're looking at reconnaissance. We're looking at weaponization. So identifying targets, building out the botnet itself, and then weaponization, trying to identify what the target goals are and how to perform those using these available resources that exist on the internet. The central three components here, delivery, exploitation, and installation, that's where the botnet is actually interacting with remote systems. It's going out, it's trying to find targets, victims, hosts, whatever you want to call that, infect them, deliver a payload, and then exploit that system. Finally, on the right, we have command and control and actions on objective. Those are long-term persistent actions that the botnet can take. So once it's been infected into millions of machines, the botnet operator or operators can come up with new ideas, new actions that they want to take, and have a command and control system over IRC or HTTP that allows them to provide new instructions to those remote systems. We're going to focus on the central three components here, that delivery, exploitation, and installation. So step one would be logging onto a system, right? Trying to gain access through stolen or guest credentials. Step two, execute a predefined sequence of commands. So that would be send the actual shell commands that will install my payload. And then three, install something that is persistent, right? Maintain that there. So Andre and I set up a demonstration environment that consisted of Amazon EC2 instances, and they were running Cowrie, which is a SSH telnet honeypot, and a command and control EC2 instance that was running NiFi, and this was 1.3.0. Quite a bit of security enabled, because the last thing you want to do is set up a honeypot, think you're smarter than the attacker, and then they turn it around and use it against you. So one of the things that we wanted to really talk about here was the approach of flow design. It's very easy to look at the NiFi canvas and think, I'm going to build from the beginning to the end. I'm going to have step one, I'm going to connect it to step two, I'm going to connect it to step three. What that leads to is you start solving problems in piecemeal, which can be good, right? You want to divide and conquer large problems, but you're starting from zero and you're trying to build every step out. What we recommend is think of it like a maze, right? When you try to solve a maze, especially on paper, you want to start at the end and work your way backward. So when we're designing a flow, we think, what is the end result that we want from this flow? And then how can we get there from what we start with? Don't be limited by what your previous flows looked like, right? There are best practices, there are patterns to follow, but it doesn't mean that whatever I built yesterday or last year is going to be the right solution for this problem. So I want to start with my objective and work backward from that. So, logs, logs, logs. This is Andre's slide, and he really gets excited about it. We had a MiNiFi process group. That was my alarm to come down here and get ready. We had a MiNiFi process group which was tailing files, and so this is tailing the logs. We're treating the logs as abstract data, right? So, and I'll show you in a couple slides what a Cowrie log file looks like. But essentially, we're pushing to Amazon S3 via a put S3 object processor. So we're interacting with the AWS API. But we could just as easily do this with NiFi site-to-site protocol or a raw HTTP invocation. This is just to demonstrate the extensibility of MiNiFi, that you can find a number of ways to communicate back from your edge nodes to your central command and control. And what's the data that we're actually bringing in? So Cowrie writes single-line JSON entries for every action that the other user, right, in this case it's an attacker, is trying to communicate to our system. So it would include the username and the password, what commands they tried to execute, what parameters they passed those commands, and if they tried to download any files. So NiFi comes with processors excellently suited to this type of data. We have split text, we have evaluate JSON path. So it's machine readable, it's also human readable. We can start splitting the log files by individual lines, and we can evaluate JSON path to pull out the pieces of information that we're interested in. So this is an example of a log file, and you can see that we have an event ID, which is some hierarchy of operations that happened within Cowrie. We have the timestamp, and then we have the message, and you can see that this is just exactly what you would see on your terminal, right? Command failed, you can't run cat proc mounts. This is the flow that was running on the central NiFi instance in EC2. So this is, you can see list S3. It's listing an S3 bucket and seeing all of the objects that have been put there. Fetch S3 object takes the flow file from list S3, iterates over those listed objects, and fetches them into the system. So now you have a flow file per object, and the content of that flow file is the content of the S3 object. We then split the text and evaluate JSON path, just like we talked about, and then send it off. Invalid logs go to a process group, and valid logs go to a process group. So we've looked at the data that we were getting. What are we actually trying to achieve here? Is anybody familiar with this image? It's titled Blind Men Describing an Elephant. Okay? And ironically, I work for Hortonworks, and we love elephants. They're all over the place. If you look at a very specific part of your problem, you often fail to grasp the entire scope of that problem. Okay? That can also apply to, I have a problem, I only know of, or I only think of one way to solve it. All right? We're not saying copy everybody else. We're not saying that there's nothing new to invent. But there's definitely value in being aware of existing attacks on these problems, existing solutions, and how those solutions have evolved over time so that you're not spending time reinventing the wheel or failing to find a valid solution to this problem when one exists somewhere else. Looking at logs and only looking at logs leads to isolation. You won't have a meaningful view of what's actually happening on the system, right? If I just look at a single line of a log, I may not understand the context around that. What was happening? It's a session, right? The user, or the attacker in this case, is trying to do something. They're a person. Whether it's the botnet actually executing those scripts, a person developed that. So think about it in that context. Think about the surrounding, the history of what's happening, what their goals are, so that one minuscule piece of data doesn't define your entire problem scope. The bots do use semi-random values sometimes to try and make exact matching difficult so that if we have some kind of protection in place, it doesn't hit every time. And we'll talk about how to fix that as well. So our solution was to treat the logs just as data. Okay? Everybody in here, there are plenty of sessions this week about machine learning and deep insights and all kinds of stuff. Treat the logs as data and apply the thought processes to, if we're getting non-malicious data in, right? Non-attacker data. We need to get insight from that. The same thing we do with the logs from these attackers. So if you're looking, excuse me, the left and the right, you can see these are exactly the events, the records that are coming in from Cowrie, and you can see that somebody's trying to run BusyBox. And now LSUCT on the right and XUSRH, those are the semi-random values that we talked about. So if it was just a strict text match, those two events wouldn't be correlated at all, right? It would, if you compare A to B, they're false. It's not the same. But those semi-random values to try to bypass protection systems is familiar. Everybody in this room has used email. Everybody in this room has gotten spam, right? If it was the same subject line every time or the same sender, you'd be able to block it once and never have to worry about it again. So the attackers come up with, it's an evolution. It's an arms race. They come up with ways to get around that, and then the protection has to increase as well. So here we're looking at a couple of emails in a Gmail inbox and seeing that there are patterns that are similar, but obviously the text is not identical. Well, email, while spam is not a solved problem, there are obviously approaches we've taken to try and minimize spam. So what are those? Well, one is called fuzzy hashing, right? Locality-sensitive hashing. So locality-sensitive hash, if people are familiar with a cryptographic hash, like SHA-256, SHA-512, KEKAK, those are hashes which employ an avalanche effect in order to make sure that two pieces of incoming data that are different even by 1 bit generate hashes that are wildly different, okay, significantly different, in order to make sure that if I download something and I run essentially a checksum on it, I'm sure that I've downloaded the exact bits that I wanted and that the developer or delivery system wanted me to obtain. If even 1 bit is wrong, the hash will be wildly different and I'll know that something's wrong. A locality-sensitive hash is the opposite. If I have 2 pieces of input that are identical, I'll get identical hashes out. But if I have 2 pieces of input that differ by a few bits, the hashes will be very, very similar. And it gives me an ability to understand near duplicates or fuzzy hashes. These are used everywhere from genomic processing to, as we said, anti-spam, and in a lot of content identification and image identification as well. Combining that locality-sensitive hashing with the NiFi flow that we had allowed us to immediately identify patterns in the botnet execution and very, very rapidly classify them alongside existing patterns that we'd observed. There's a demo here, but it's on Andre's machine, so we're tight on time anyway. Treat everything as data. We talked about that. Don't worry about, well, this log came from this kind of machine or this kind of generating format. With the capabilities of NiFi, you can bring that in, you can standardize and normalize it, you can convert it to whatever format you want. So if you have tools that only identify or only accept a specific format, that's no longer a limiting factor, right? You don't have to write custom code to do that translation. You can accept data from multiple different endpoints in different formats and normalize it and bring it in and increase the insights that you're getting, because if you do machine learning, deep learning on very small sample sets, you're not really getting the benefit of those algorithms. But if you can aggregate multiple data sets and improve the quality of data that you're getting, or at least the scale of data you're getting, you can improve the quality of the insights thereof. Be flexible on how you build your data flows. We talked about that with working backward, identifying an objective or a goal, and seeing what you can do to get to that point, and using MiNiFi to aggregate data at the edge. So again, MiNiFi was in use here to coordinate between Cowrie and the communication back to the central NiFi data system. You could use that in multiple hops if you want. In this case, they were all on EC2, so it was pretty simple. But you could also use MiNiFi to do initial tagging or geo-enrichment based on IP, or time-sensitive operations such as windowing and aggregation. You can do all of that at the edge and wrap that up and move some of the processing that is not dependent on things like machine learning, data science, out to the edge so that you already have that information. You have some of that metadata aggregated when it comes back to the sender. Ways forward from here include things like automatic IP blocking or firewall rule updating using machine learning from the information that we're aggregating. updating the signature definition lists based on new signatures that are coming in. And this could even be used to analyze like epidemiology and spread vectors. So if you start to see a specific pattern originate from IP addresses or from servers in a specific location, it's not attribution, but it is a piece of information that supports attribution to start saying, okay, we see this pattern evolving here. Now we're starting to pick it up over in this different cluster. Now we're picking it up over in this different cluster. And you can follow the spread of essentially an idea the same way that a virus spreads. These are a couple great articles that discuss how the malware evolution occurs, how the fuzzy hashing supports that. And then at the bottom, you'll see this is actually the template and sample. So anybody can download this and run it themselves. And you can have that up and running. I mean, you can use an EC2 instance. You could use a local NiFi and MiNiFi instance if you want to. I don't recommend letting botnets target your personal machine, but that's up to you. But you can do this. You can replicate our results. You can possibly see differences. I mean, things are evolving all the time, and you may get different results than we did. We're happy to communicate about those as well. Thank you very much. Again, apologies for the late start, and I'll take questions now. Thank you. No questions on an 8-minute presentation. That's odd. Yes?
3 or 4 slides back, we were talking about use MiNiFi to aggregate at the edge.
Yes.
I wonder if you could maybe elaborate a little bit, because I have an environment where I don't have MiNiFi.
Okay. Sure.
I was wondering if I'd missed a trick there with MiNiFi breaking out that.
Okay, so the question for anybody who didn't hear was about, in general, MiNiFi at the edge doing the data aggregation. You have a central NiFi instance. You're not sure how much processing you want to do there. Can you move that to the edge with MiNiFi? Okay, that's a great question. MiNiFi is definitely suited for that. There's a balance. It's not a black and white dichotomy. There's a balance between how much processing you want to do at the edge and what your resources are and what your time sensitivity is. So if you want to do really heavy processing, machine learning and PySci models and things like that, you probably want to do that back in your data center where you have the more robust machinery and hardware to perform that activity. If you want to do early tagging, so things like flow file prioritization based on some kind of signal, right? I see that if I get let's say I had a Cowrie log entry and it was login success, that's probably something I want to know about before failed on A, failed on B, failed on C. So if they're just brute forcing random commands and they're failing every time, that's fine. That's stuff that I want to learn from and I want to aggregate all of that, but it's not an immediate concern. If somebody's actually guessed the password to my system, that's more of a concern for me. So you could do that prioritization at the edge with MiNiFi. You could do filtering. You could say there are certain records that I don't care about, and I want to write just a local buffer. So I can go back and check an archived log later, but I don't care about that for my processing. Was there more to the question about actual, like, computationally intensive processing, or? Yeah. So you absolutely could do that at the edge, and the locality-sensitive hashing is not really that expensive of an operation. So think about, like, if you calculate a SHA-256, that's a very fast operation, and you can do that on minimal hardware. The same thing applies to the TLSH and SSDeep locality-sensitive hashes. So those are absolutely things you could perform at the edge. In this case, we did it in the center just because MiNiFi was there to demonstrate the ingress of data, but not the processing. But you could absolutely move that to the edge, yeah. You could also do that if part of that processing is sensitive, something you don't want to share with your central data cluster. So you could do anonymization or sanitization of data at the edge and then send it back to central data. Yep. Any other questions? Yeah, please.
You're watching Honeypot, and you can probably assume that a lot of the activity is bad guys.
Yeah.
In real world, that's going to be hopefully a negligible amount of data. But thinking back, I mean, I can't remember the exact title of the talk, but it was identifying botnets.
Yeah.
How do you take what you've learned here, and then maybe how do you match that against real world data?
That's another great question. So the question was, the title of this is identifying and classifying botnets. But botnet activity will hopefully be a negligible percentage of the activity on a legitimate server. So how do we apply the lessons here to a real-world scenario of having active, valid users on a machine and hopefully identifying just the botnet parts? So that's a great question. Because of the learning from this, the title is about classifying botnets into families. So like this family performs these types of actions, this family performs these types of actions. So comparing activity against signatures patterns basically of, oh, this looks like botnet A, this looks like botnet B, this looks like it doesn't match anything. So maybe it's a new evolution of a botnet, or maybe it is legitimate user activity. Being able to rapidly match those patterns because it's a simple hash comparison is very fast. It's a heuristic. It's not 100% accurate, but it reduces false positives pretty strongly. You could apply the same learning, though, to legitimate user activity. So take a server that you know has not been compromised, or you know as best you can has not been compromised, and take that activity pattern and generate the same types of signatures. So now you can say, okay, I have some unknown sample of a series of activities. Let me compare it across all of my known signature patterns. It comes up with 0%, 0%, 0%, 1% likelihood of being these botnets and 85% of being legitimate user activity. It's not a 100% clean slate, but you could probably deprioritize evaluating that data as opposed to a section of log that said this is 60% similar to this botnet family of activity. And those comparisons are very rapid. I mean, they're literally on the order of magnitude of milliseconds to do the hash comparisons. So this is, again, this wouldn't be your entire SIM system. This wouldn't be a user audit system. But this would be a rapid prioritization and filtering of this looks like suspicious activity. Have somebody do a forensic investigation on that. All right. I'll be available throughout the day. Again, I do apologize. I appreciate everybody coming and especially staying for this long. That really speaks to the level of interest in Apache NiFi and the real-world applications thereof. So thank you very much.